Oops, I just turned on. Felicia. Oops, it just went off again, or something. I don't know what happened.
Did you just disconnect?
Okay. So we left off yesterday and we were talking about what's new or interesting, or maybe neither, is we're working on solving situations, and it's the inverse steps in reverse order. The inverse of addition is the inverse of multiplication. The inverse of logarithms is exponents. Yep, you got it. You know what you're doing. Okay. Page. Hey, Menominee, how you doing?
Pretty good. How are you?
I am well. Okay, so we were on number 6 here, transformations. Well, one place that you run into transformations is computer graphics. We can imagine the scaling transformation as an animation that stretches out the parabola vertically. This transformation is followed by shifting, moves it upward. If we wanted to reverse, we could slide down and then shrink. Let's look at this one right here. 3x squared minus 12x plus 1. Let's take out our notes. And I'm going to tell you that the vertex for this parabola is at the point 2, negative 11. So let's start there. 2, negative 11. We're just going to do some practice graphing here. Okay, now according to the formula, it says the formula is 3x squared. So the only part we need to start graphing once we have the vertex is the scaling factor. In this example, the scaling factor is positive 3. See if the person sitting next to you knows what that means when we go 1 in each direction from here. Go. So let's put down our first dot. We go over 1 positively. And what should we do once we go over 1 positively? Go 3, right? Because it's 3 times as big as usual. But why 3 up? Because it's a positive 3. There's a point that you automatically know goes along with that. What point is that? Back 1 and up 3. Okay? What's the next point after that? Back 2. What's 2 squared? 4. 3 times as big. oops, I'm sorry, we should have been here and here. 3 times as big as 4. 3 times as big as 4. 12. So if we were down negative 11, we're going to be at the point 0, 1. So we're going to go 3 times as big as 2 squared. And we're going to go 3 times as big 2 squared in the positive direction. So our parabola is going to look like that. Now, the only problem is that in our story, we don't know that we start out at over 2 down 11. You don't know that. Well, we'll discover why that is in just a little while. I mean, not today. What transformations must be applied to L to obtain 3x squared minus 12x? So, we start with, come on, Kevin. We start with L of x, which we know to be 3x squared minus 12x plus 1. Now, they don't tell us what the step is here. They just tell us that the result is 3x squared minus 12x. What did we do to go from 3x squared minus 12x plus 1 to 3x squared minus 12x? We subtracted 1. So, minus 1. And we get m of x. Is this an input shift or is this an output shift? It's not connected with the x, so it is an output shift. What are we going to do on our graph because of that?
Shift it left or right, one of the ways.
What did we do? Minus 1. So where does our vertex go on our diagram? Down 1, right? So over to negative 12. Good. So that moves every single one of our points down 1. Now, one thing that's interesting about this is that it moves it so that this point over here goes through 0, 0, which tends to make Madeline very happy because she likes that point 0, 0. She likes to start at the beginning. Okay. Next. Using a graphing calculator or app, find the coordinates of the vertex of the parabola m of x. Well, we just said what they are. What were those coordinates? In this case, the center was at over 2 down 11. Now the center is at over 2 down, not center, vertex, over 2 down, what did I just say? 12, good. So that's where our center is now. B, how would you move the graph to get the vertex to land on the origin? So right now we're at 2, 12. Okay? We're at 2, 12. We want to go from over 2 down 12 to over 0, down 0. What do we have to do to the input? Shift the input back 2, right? And shift the output up 12 to get to 0, 0. So shift the input back 2, shift the output up 12. So, part C. What transformations must you apply in order to obtain the new function 3x squared? Let's do it in 2 steps. I think that will help us. So let's shift the output plus 12 which gets us to 3x squared minus 12x plus 12 and then shift the input negative back to which means to the left 2, which means positive 2. And the way we do that is we would write 3x minus 2 squared minus 12 times x minus 2 plus 12. And that will get us to 3x squared. Now let's go through the math to see how we get that. X minus 2 squared is x squared minus 4x plus 4. Multiply that by 3 is 3x squared minus 12x plus 12. This is minus 12x plus 24 so if we subtract that, we get 3x squared plus 12 minus 12 is 3x squared. Number 8. Looking back at questions 6 and 7, start with the parabola L of x, which we know is 3x squared minus 12x plus 1. Move the parabola blank 1 unit to land on the parabola M of x, which is 3x squared minus 12x. Which direction do we have to move it to get to 3x squared minus 12x without the plus 1? Move it. Which direction? This is output, down, right? Input is left and right. Output is down 1. Move the parabola m of x left 2 units, up 12 units to land on the parabola n of x. Let's see how that works. N of x is 3. Let's factor out of 3 out of this, and we're left with x squared minus 4x plus 12. Now, if you see this right here, x squared minus 2x plus 4. This is a square right here that it has the dimensions x minus 2 times x minus 2. So they call this completing the square. Oops, I'm sorry, this should be minus 12 here. This is plus 4. Let's go through the directions on how to complete the square. That'll help you. This shape is a square. The first step is to get the lead coefficient 1. So to do that, we'll start with 3 times x squared, and then if we factor a 3 out of 12x, what do we have? Minus 4x. So now we know this part here is x squared. These two parts right here add up to negative 4x. So step 2 is to take half of the x coefficient. I'm going to have to ditch this pen. Blue is dead. Long live blue. So half of the x coefficient, negative 4x, gives us negative 2x. And I split it into 2 spots there on my graph. Well, this part here must, if this is x and this is x, this must be minus 2, and this must be minus 2. So these 2 parts always will be the same dimensions, otherwise it won't be a square. So we would say 3 times x squared minus 4x. What do you get when you square those two? Negative 2 times negative 2. Four. Let's see here. So step 3 is to square that number right here. Square that number. So if we add 4 here, we have to subtract 4 on the back end. Four times 3 is negative 12. So our n of x was 3x squared. Our p of x was 3x squared minus 12. Our q of x was 3x squared, 3x minus 2 squared, which is 3x squared minus 4x plus 12. And our r of x was 3x squared minus 4x minus 11. Let's rewrite this part here as 3 times x minus 2 squared minus 11. So our graph from 0, 0, when it was like this, moves to forward 2, down 11, and you get this graph right here. We're going to do transformations for the rest of the course, so I don't think you have to have that nailed down quite yet. The next lesson gives a practical example of transformations. Let's look at the original function here. Dwayne buys a case of ice cream bars and takes them to the beach to sell. What's a reasonable price for an ice cream bar at the beach?
Depends on where you are.
And it depends on what the weather is like. If you tried to sell ice cream bars down at Half Moon Beach today, you couldn't give them away. First of all, there's nobody at Half Moon Beach today. But there was during the summer. On a hot summer day, you could sell a lot of them. Well, that's what Dwayne is trying to figure out. What would be a good price for a candy bar? What happens if he sets the price too high? And if he sets it too low? Or he loses money? Dwayne's total profit for his ice cream venture can be modeled using a quadratic function. This is 10c. Can be modeled by the function p of x is negative 4.3 x squared plus 27.52x minus $20.78. Dwayne's friend Alondra thinks that he should sell the bars for $3, but Dwayne insists on selling them for $2. So the way we would find out which one is right is to substitute in $3 and $2. So, these people on this side of the room, you're going to sell them for $3, and these people on this side of the room in Menominee sell them for $2, and let's get what the price of a ice cream bar should be. Yep, that's all you do. Just plug it in. What'd you get, $3 people? Or $2 people? I don't care who answers first.
I got 1706.
1706, and that was for the $2 people, right?
Yeah.
2308, that was the $3 people. So, who made more profit? Those that sell them, or which one would you get more profit? Selling them for $2 or selling them for $3? $3, okay? Is that the best price to sell them for? Well, one of the ways that you could do this is to graph that equation. If you notice, here is the graph of that equation. $2, if you sell them for $2, you end up here at 1708. If you sell them for $3, you end up here at about 20, what did we say, $23 and something? Is that the best price to sell them for according to the graph? Do the graph and let's see what you get. What's that? Are you picking on Desmos? Everybody capable of graphing that in Desmos? You got it figured out? You got it down? So the best price to sell them for according to the graph is how much? $3.20, and if you do, what do you make for a profit?
$23.25.
That's not bad. $23.25. Okay, so let's look here. Fact. If the formula for a quadratic function is written in the form f of x equals ax squared plus bx plus c, the vertex will have the coordinates negative b over 2a and f of negative b over 2a. So let's go through everything we know about our function p of x. Negative 4.3 is the scaling factor, which means the second difference is remember, it's always twice as big as the scaling factor. Okay? The next thing we know is the output shift.
Wait, where are you finding these numbers?
Right up here.
Oh, in the equation. Wow, crazy.
Output shift. Oh, I should have done that one in purple, shouldn't I? Output shift is down $20.78. So our graph is going to be shifted down $20.78. In other words, there's some kind of expenses that we have to take care of that add up to $20.78. Remember when we were dropping the rock, we added 200, right? Because we moved up 200 feet before we dropped the rock. Okay? Now it's telling us the vertex is at 27.52 over 2 times 4.3. Now, make sure you get the negative here because its vertex is at negative b over 2a. So we have to change the sign and double a. That is the first coordinate of our vertex. Hold it. I've seen that 8.6 before.
Crazy. It's D2.
Very good. So it's b over the second difference, comma. And then in our book it says f, or in this case, the other coordinate of the vertex is p of 27.52 over 8.6. So what are we going to do in order to find that value? Substitute that into
The equation.
our equation. Very good. So we're going to take negative 4.3 times parentheses 27.52 divided by 8.6 close parentheses squared plus 27.52 times 27.52 divided by 8.6 minus 20.78. And we get 23.52. So our vertex is at negative b over 2a, comma, f of negative b over 2a. Quadratic forms. I'll tell you what, let's make it a full-size piece of paper. ax squared plus bx plus c is called the standard form. The vertex form is a x minus h squared plus k. The vertex is at the spot h, comma, k. This is the output shift. This is the input shift. If this were gravity, c would be the initial height, B would be the initial speed, and A would be the half the acceleration. Take a picture, otherwise I'm going to go on. Got it? So in this example, how much money are we going to make if we sell 0 ice cream bars? Negative $20.78. That's probably to pay for the Yeti that we had to buy to keep them cold. I don't know what the $20.78 was used for. How much, well, the other ones we don't have a context for right yet. We'll have to wait for context for them in a few days. Use this fact to find the coordinates of the vertex of the profit. Verify your answer by graphing the function using a graphing calculator or app. So we graphed our function, and we found the coordinates to be $3.20 with a profit of $23.25. Number 4, write that formula in the vertex form. So we would write, does it tell us which letters to use? Nope. So P of X equals, in our vertex form, our lead coefficient is going to be the exact same number, which was $4.30. Negative $4.30. Or was it negative? I can't remember now. Yep, negative $4.30. Well, yeah, it has to be negative because there's a maximum amount of profit, so it has to be going open downward. X. Now remember, this number right here is the input shift. How much money are we going to sell those for? $3.20. Why is it negative? Because we shift right. Remember, you have to square that. And then plus, I forgot what it was, $23.52 or 25 cents?
$27.52.
$27.52? Okay, sorry. 27, no, it's 23.25 right here. No, I'm talking about this, $23.25. So the coordinates of our vertex are right here. From there, to go left 1 and right 1, we have to go down $4.30. To go left and right 2, we have to go down $4.30 times 2 squared. I don't know what that is, about $17, something like that. $18. Number 5. Now suppose that Dwayne must pay a $5 permit in order to sell ice cream at the beach. Modify the function to account for this. So instead of needing $23.25, he's going to need $5 more, right? Oh, I don't know which one they want us to use, if they want us to use the vertex form or if they want us to use the original form. Because in the original form, it would become $25.78, right? In the vertex form, it would become $5 less profit. What would that be? $28.25? No, he would have to have $5 less. His profit would be $5 less, so that'd be $18.25. So if he charges $5 more, oh, here's that vertex. If he charges $5 more, or if he gets charged $5 for that fee, it's going to lower his profit to $18.25 rather than $23.25. So if we used our original form, P of x, P5 of x will be negative 4.3x squared, I forgot what the middle term was, plus 27.52x minus $25.78. Number 6. Suppose that experience tells Dwayne that he maximizes his profit when he sets the candy bar or ice cream bars at $4. How much more money will he sell them for instead of $3.20? $0.80 more, right? So now his profit moves to $4. So if you notice, instead of breaking even at $23.25 at $3.20, he sells them for 80 cents more. So we go forward 80 cents. So it's our original function, just moved number 6. We would say it's a input shift of 80 cents to the right. Probably the easiest form of a quadratic is the root form. The root form tells us where we go through the x-axis. That's why they're called roots. We still have that same lead coefficient, which tells us that from the vertex we go down 1 over 1 both ways, down 2 over 2 both, or 4 over 2 both ways, and so on. So the root form is the last one that they talk about on this page, and they give us the two roots. In other words, we're going to not make any money if we sell the ice cream bars for what prices? According to that root form that you see in number 7. We're going to make no money if we sell them for $1 or $6, right? So if we aren't going to make money if we sell them for $1 and $6, what will the maximum amount of profit be at? It's halfway between $1 and $6. Not 3. $3.50, right?
Yeah.
$3.50. So in the root form, the vertex is at the point A plus B divided by 2. Halfway between those two values. On a hike, Sonia discovered a trough like the one in the picture. The short front side is in the shape of a trapezoid, and the open top is a long rectangle. She noticed evenly spaced markings on the inside face of the trough. 80, 60, 40, 20. At first, she thought the markings were there to measure the volume of the water in the trough, but then she realized this couldn't be the case. I'm going to show you a picture that might help you realize why that can't be. If I can find it. Not that way. I guess I have to go the long way. Let's see here. Give me a view of the medium icons. Oh, there it is. Okay, here is a measuring cup. It's not very easy to tell from the liter size, but it is easier to tell on the cup size. Do you notice that the distance between 1 cup and 2 cups is bigger than the distance between 2 cups and 3 cups? Is bigger than the distance between 3 cups and 4 cups? Why? Yeah, because the diameter got bigger. So let's look at the trough. If those if in our trough, each of these lines was talking about the volume of water in the trough, like this one is 10, this one is 20, this one is 30, this one is 40, that wouldn't make sense because there's no way if this has an area of 10, this also has an area of 10. Does that make sense? No, you can't possibly have the same area. So those two can't be talking about amount of water in the trough. The other thing that's true is that it couldn't be talking about how long it takes to fill to that spot. Like this is 10 minutes to fill to this spot, this is 20 minutes to fill to this spot, 30 minutes to fill to the next spot. You couldn't use it in order to see how long it takes to fill it. So that can't be why those lines are on the trough. A clear plastic measuring disc has a similar shape as a trough. It's 20 meters long. Its face is a trapezoid. The dish is pictured as follows in the following diagram. And so here it is, 20 centimeters long, 3 centimeters at the bottom, 9 centimeters at the top. Did it also say 3 centimeters high? Can't remember. Yeah, 3 centimeters. What? It said it, but they didn't draw it, did they? And it's 20 centimeters this way. The volume is the base times the height. Well, here's the height. We need to know what the area of the base is. It's a trapezoid. And the area of a trapezoid is the height, which is 3. Notice these two h's are not talking about the same figure. Times the average of the bases. So in this case, the area of the base will be 3 times 3 plus 9 divided by 2. What's 3 plus 9 divided by 2? 6. 3 times 6 is 18. 18 times 20 is 360. So this shape right here holds 360 cubic centimeters of water. We'll start there after our break.
straight hair.
While you were looking,
I gotta get these straight before you're marking.
my hair, like, it becomes half the size.
My hair, she's like, so you can get straight hair. I just need to set up hair products. There's like, I don't know what they're called, but I really want to get some and like try and
I've tried one before. It was like a banana avocado, but then my mom had a sister with a comb and like comb out the banana. It's like I like blended it and twisted it out. I gotta wash that.
you should get that. I got like 8 inch or 6. Did you just cut it? How much did you have?
The time before that, when I get my hair cut, it's always like 6 inches, and no one notices. I'm like, no, I promise. It didn't happen. It's 2 inches.
I usually is like an inch or 2 off because I want my hair to be long, but I also want to get rid of my split ends, so it kind of just. I this time next year I'll do that. Like I'll like usually my hair for I've cut my hair in 2 years. Well, since my dad was. How did he close to me? Because I was shedding that. Oh. So he said he wanted me to cut my hair. Okay. I just make sure that I get like a big.
Some people like, yeah, some people
Well,
like,
I mean, I thought
maybe allergic to like and like just people chew that people just chew gum around them. Yeah, so I was like,
I didn't retake the test, but I get 100 on home. I don't know why I have
it's like a seed that's every time. That's a lie. Wait, I know.
The rhyme city.
To help you see that the for a trapezoid, you can find the area of the trapezoid. If you take this part here and flip it around, it will completely fill in this spot here, which would make the top part 6 long, the bottom part 6 long, and it's still 3 tall. 3 times 6 is 18. So you can see how it gets to that shape. The next question asks, how much does it hold when it's completely full? 360 milliliters. Does this answer seem reasonable? Okay. So, now it's going to ask the question. We aren't going to take the volume overall. We're just going to take the volume that there is as you start filling it up. In other words, as H, the volume, as a function of how high it is in the trough. So we have volume as a function of height is $20. That's how thick it is, times H squared plus 3H. Or in other words, if you multiplied that out, you would get 20H squared plus 60H. Number 4, use a graphing calculator or app to graph that function. Where is it? There it is. So when we do, we get, goes through 0, 0, which makes sense. It's got no output shift, so it goes through 0, 0. And it's stretched out 20 times as far. So if you go over 1, instead of going up 1, you go over 1 and up 20. That's not right. That's 75, isn't it? No, 80. Oh, I forgot to multiply it by 4 times as big. If water is poured into the dish at a constant rate, does the water level rise at a constant rate? In other words, if you put in 100 milliliters, if you put in 200 milliliters, if you put in 300 milliliters, notice the distance between 0 in the first case is 1.93. In the second case, it's about 0.8. Then it drops to 0.653. Why didn't I put down 400 milliliters?
They can't hold that.
Yeah, because it only holds 360, so I can't go higher than 360 because that's all the more that it holds. So does it fill at a linear rate? No. It gets higher faster at the beginning, and then it slows down as you keep going. Letter B, the second part. Can you identify a feature of the graph that tells you it does not go at a constant rate? What about this graph tells you it can't be filling at a constant rate? Because a constant rate is a sign of a linear graph, and this is not a line. Part 5. Suppose you want to draw markings on the face of the dish to indicate water levels. At what heights would you draw the 100? How many centimeters up? 1.19, right? 200 centimeters. 200 milliliters. How far up would you draw it? 2 centimeters. And 300 milliliters. How far up would you draw it? 2.653. Number 6. They give us something, but they don't tell us how they got there. Let's start with the standard form, which is volume as a function of height is 20 h squared plus 60 h. And let's get it into the root form. If we factor out the 20, we're left with h squared plus 3h. What can we take out of this part right here?
No, the H.
H.
That was dumb.
And we have h plus 3 left. So if we're going to graph that, this tells us we go through the point 0, 0. This tells us we go through the point, oops, wrong side, Kevin. Negative 3, 0. So our minimum volume is halfway between those two, negative 1.5. I don't know what that minimum volume will be, but we keep on increasing so that at 0, we're at 0, and at 3.6, we're at, 3 high, we're at 360 milliliters. Now it says, if you take that h squared plus 3h and just say, well, let's see if we can get different values for the volume of our trough. The first one that they say is, what would happen if that volume would be, what does it say, 10 minus 10. So here's our tic-tac-toe. H squared minus 10. Obviously, this part here is going to be h by h. But how do we get negative 10? One of the numbers is going to have to be 5, and the other number is going to have to be 2, correct?
Yeah.
But one of them is going to be positive, and the other one's going to be negative. Since this is a positive sign, the bigger one is positive, which makes the smaller one negative. This is negative 2h, positive 5h. And you get h squared plus 3h minus 10. Page. What page number is this? 149. In the second case, they tell us we have h squared minus 40, and one of our numbers is h minus 5. So we have h squared minus 40. How do we get h squared? This number has to be h. How do we get negative 40 if one of the two factors is minus 5? Negative 40 divided by negative 5 is positive 8. Notice that here you get 8h. 8 times h is 8h. This is minus 5h. So you have h squared plus 3h. You see where the 3h came from? Positive 8, negative 5, minus 40, which matches what they said in that first one. Second one, they say the two numbers are going to multiply equal negative 18. If one of them is positive 6, what's the other one? Negative 3. They say the two numbers multiplied equal negative 4 and added equal 3. So we've got negative 4 h squared, so this is h and this is h, but these two numbers here have to add up to negative 3h. So one of them is going to be negative and the other one's going to be positive. What two numbers are 3 apart but multiply equal 4? 4 and 1. If you don't know how to do that one, you can go to Desmos and you can graph it. Oops, I'm in the wrong spot. Oh well. Factoring. Oops. You can graph it. So we would say h squared, let's say x squared, plus 3x minus 4. And notice it tells us what the two spots are, negative 4, positive 1. So if you graph it, you can tell what the roots are without having to factor. In my mind, factoring is way over stressed. Because look at this one right here that we did in the last lesson, where we were talking about the selling the ice cream bars. would have we been able to find these two coordinates by factoring? $87.5, $5.52.5 by factoring? Not very easily. Because if you notice, we've got that negative 4.3 out front. That makes it hard to factor. You have to divide everything by negative 4.3. Last one. H squared plus 3h minus 28. So if you notice, the two numbers are negative 7 and positive 4. Use patterns and or shortcuts to factor all the following quadratics. Well, I should ask you this question. Factoring the way you learned it in high school, give me a 5, 4, 3, 2, 1 on that. 4, 5, 5, 4, 5. What do you got, Jake? I got nothing. Don't remember it in high school. I don't remember high school. That was in grades 9 through 12. Although in Altoona, did they start at 9 or?
I'm not sure.
Oh, you weren't. I thought that's where you went.
I went to Memorial.
Oh, you went to Memorial. Okay. Who was the person that from our last class that went to Altoona with you?
Dylan Strasburg.
Oh, Dylan. I knew he sat at this table.
I probably forgot because he never showed up.
Oh, come on now. Everybody, how about you guys? Menominee, I didn't see your fingers on factoring.
I don't remember. It was like 4 years.
I don't remember factoring. Do you remember high school? Okay. The thing about it is, if you don't know how to do it, you can always go to Polysimul 2. So if you go to Polysimul 2 on your calculator with this first one, and you put in, so I'm looking for polynomial roots, you put in 1, -1, and -6. It tells you that the two roots are, so if you start with x squared minus x minus 6, it tells you the roots are x equals 3 or -2. So the factors are x minus 3, x plus 2. Remember, you always change the signs from the way they were given. I don't know. I think factoring is way overrated as a skill that you need to be able to do. They teach it in this class just because when you get into the university, they stress it a lot. Page 151. Consider the daily electrical use of a typical household. Does the power used vary throughout the day? It says sketch a graph of the power used by a household as a function of time. Make a graph for your house. I'll make a graph for my house. I'm going to start with 0 is midnight and 24 is the next midnight. So then 12 would be noon. Depends on the day because we don't do the same stuff every day at my house. There's my sketch. I don't know what yours look like. One of the things that you have to make sure is that your label at the beginning, or wherever you started at the beginning, is where you finish at the end of the day, because the next day you're going to start at that exact same spot. So at our house, during the night, we don't have a lot of electricity that we use, because we're in bed, sleeping. I suppose the furnace runs, the refrigerator runs, freezer runs. all those things that have timing devices in them, like your microwave, TV, right? That uses electricity even when it's off. So it remembers what all the channels are that it knows. Then we wake up, take a shower. We have electric water heating at our house. Then it goes down during the day. Sandy's there. I don't know what she does. That's why I'm not real sure. But she uses electricity. I know that. And then I come home. We make supper, watch TV, and then we go to bed. Is that kind of how yours looks? About the same? Page 151. The power is measured in kilowatts. Now they're talking about a different situation, though. The power in kilowatts drawn by a large lighting array is ramped up gradually according to the function P of T is 0.4 T. So I have a question for you. How much power does it use when you turn it on, or just before you turn it on? 0, right? And then an hour later, it uses 0.4. 2 hours later, it uses 0.8. Got it? It gradually ramps up. Is that a linear function? Sure looks like it, doesn't it? It says sketch the function from 0 to 6. At the beginning, it uses 0. How much will it use at 6 hours?
2.4.
Very good. Do you know how he got that? No. Took 6 times 0.4, because the equation here is power as a function of time is 0.4 T. So each hour, it uses 0.4 times as much power as the amount of time that has passed. Part B. Power is a rate of change in energy. Energy is the area under the graph. So let's take the area under the graph for just any old time. Right here. So this is a particular time. What shape will this area be in? What shape is that?
A triangle.
Very good. How long is the triangle this way?
3 hours.
Well, I said any old time. So it's time in that direction. Area is 1/2. Remember, that's the area of a triangle, right? This is T. How tall is it at that point? Would you agree it's 0.4 T? So area is T times 0.4 T. What do you get for an area? What's half of 0.4? What's T times T?
T squared.
Very good. So, what they're saying is the amount of energy, which is the area, as a function of time is 0.2 T squared. So if the amount of energy we're using increases by 0.2 each hour, the amount of power that we're using, if the amount of power that we're using increases by 0.4 per hour, the amount of energy that we're using increases by 0.2 T squared. Next one. Now it says, a ventilation system draws power from the grid, but the power is supplemented by solar panels. As the sun rises, the panels gradually reduce the amount of power from the grid. So now our function is going to be starting at 2 and decreasing by 0.6 per hour. Now, we want to figure out the area, the amount of energy that we have. What shape is that?
A trapezoid.
Very good. Let's turn it this direction so that we can get the dimensions of the trapezoid. This part here is 2. Everybody agree with it?
No.
This part here, from here down to here, is T. How far is it across the top? .6T away from 2, right? 2 minus 0.6T. So what's the area here? Area is the height, T, times, remember we average the bases, so it's 2 plus 2 minus 0.6 T, which is 4 minus 0.6 T divided by 2. Two minus 0.3 T times T. So energy as a function of time is T, or negative 0.3 T squared plus 2 T. I multiplied it out. When will the total energy consumed equal 3 kilowatt hours? How would we find the answer to that question? We could just plug in different values of T. Now, can we, like Madeline said, can we solve that for T? If we know the quadratic formula, we haven't used that yet, though. How could you do that? Easiest way? Graph it. Desmos, very good. Negative. Where are we? Is that the right one? Here it is. Negative 0.3 T squared plus 2T. Okay. And when we do, we can see it's going to consume 3 kilowatt hours of electricity after 2.279 hours and after 4.387 hours. Why 2 spots? Well, remember, it's making energy at the same time, right? So after a certain time, it will be making more energy than it's using. If we keep on going on our graph here, do you notice this line is eventually going to cross there? On the graph, you can see that it crosses after 3 1/3 hours. So after 3 1/3 hours, we're going to be making more energy than we're using, which would be about noonish, somewhere around noon. Now, it says we're going to keep on gaining energy forever. Is that really true? Because what's going to eventually happen in the winter, say about 5 o'clock? Dang, sun is going to set, and then you can't go fishing anymore. I'm not saying that I'm bitter or anything like that, but so eventually you're going to run out of sun, and so you aren't going to keep on losing energy forever. They're just modeling it for a little while that the energy is going to increase like that. It'd be nice if it would forever. The other thing we could have done is we could have put the 3 in here, and when we did, oops, it was -3, sorry. When we did, it would tell us where we crossed the x-axis. In other words, we could have shifted our graph down 3 and still gotten the same correct answers, 2.27 hours, 4.387 hours. Either way, we would get the same answer. Either substituting in for 3 or taking our original equation, E of t equals -0.3t squared plus 2t, and then move the graph down 3, and that'll give us the roots. Oh my word, I closed the door on you just in the nick. Sorry about that. I told you why we have to close the door, right? They gave us a big stink about it.
So that we don't get to word out. That's a crazy person.
Last thing, chapter 11. Before Galileo's time, it was commonly accepted that heavy objects fall faster than lighter objects. Around 1589, Galileo challenged that notion by hypothesizing that objects in free fall will fall with the same acceleration regardless of their mass. Let's look at YouTube, and let's find Galileo and Pisa. Here we go. Why is that not making noise?
Galileo's year. The United Nations declared it the International Year of Astronomy in honor of Galileo's achievement 400
Okay, that's not the problem.
when the Italian scientist aimed a telescope at the night sky for the first time. But we also remember Galileo as the father of modern
Oh, it
physics.
says, no.
And here in Pisa,
What am I doing wrong?
Galileo was born, we immediately think of his investigation into the force of gravity. Galileo wondered about...
Hasn't this happened before?
Was falling straight down. Suppose you had a very heavy ball like a bowling ball, and another ball of the same size and much lighter, like a volleyball. Which one would hit the ground first? The ancient Greeks had thought about that problem. In fact, Aristotle had said the answer was obvious. He said that the heavier...
Oh, well, let's just put in a closed captioning and then, oh, French. I don't think that will be good.
But Galileo had a different idea. He said that regardless...
They are indeed in French. Not good. Anyway, here's the two things. Drop a bowling ball, drop a volleyball. Why those two? Because they're roughly the same size.
Galileo got his first teaching job.
Hey,
at
there's
the University
Pisa,
of
the
Pisa.
lawn on
With
Pisa. I'm not sure what the
nearly
N
in his
stands for
backyard,
there. I should
it
turn
must
off
have been
those closed
incredibly
captions.
tempting
They aren't
to
happening.
drop objects
Why did he
at
drop it
different
off the
heights from
Tower
top
of
to tower,
Pisa?
watching them plunge
'Cause the darn
7
thing is
meters or
crooked.
nearly 200 feet to the ground below, and seeing if they really do land at the same time. Historians say the story of Galileo and the tower may be more legend than fact. It's quite possible that
You can hear it?
did perform
Are you
the
just
test here
hearing
at the
hearing
famous
voices
tower.
in your head?
But earlier this year, this
Oh.
man did. For Professor Steve Shore, 2009 was the perfect occasion to demonstrate Galileo's ideas. And earlier this year, that's exactly what he did. And he did it in style. There were musicians in period costume. There was an actor dressed as Galileo himself.
Holding a microphone,
And
which
more people dressed as the
that was an old-style microphone back in
professors,
1589.
the ones who would have made fun of Galileo for his crazy ideas. Unfortunately, it started to rain, but the demonstration went ahead. Professor Shore climbed up the 293 steps to the top of the tower, carrying jugs of water of different sizes. Now, as I mentioned, it was raining, so just try to ignore my umbrella there at the top of the frame. There's Steve Shore at the top of the tower, with a bottle of water in each hand. And now, watch carefully. Professor Shore repeated the test several times with bottles of different sizes. In this drop, the heavier bottle is more than 3 times larger than the lighter one. If the real Galileo had been here to see all of this, he would have been pleased. He was right. Aristotle was wrong. The bottles crashed to the ground at the same time. Galileo had shown that the rate at which a body falls is independent of its weight. With the work of Isaac Newton about a century later, we had a more complete explanation for why that is. It's true that the heavier a body is, the more strongly the Earth's gravity pulls on it.
Here's another one.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time.
The other thing that you notice is it fell kind of slowly because the moon has less gravitational attraction. So they did hit the ground at the same time. There's one more I want to show you, and that is feather in vacuum chamber.
Exactly the same in this chamber until there are about 2 grams left.
So here's the vacuum chamber. Obviously, it's not a vacuum right now because
Part of its history. It was built in
the
19th
guy's in there and he's alive. Good one.
test facility to test nuclear
Okay. He does a lot of talking here, so I'm going to fast forward some. So you see the feather and the ball are both hoisted up inside the chamber.
30 minutes. But once it's
They spend a lot of time building the suspense. Oops. Went too far. Okay, so they get unleashed electronically at the same time. And because there's no air, obviously they aren't falling this slowly real. They're doing it in slow. And they hit at the same time. And they're all surprised. Now, you can see why Aristotle thought that the feather falls slower. He was basing it on the weight, but he was ignoring the fact that it was falling through air. So that's why if you take the air away, all objects fall at the same speed. let's get back to Galileo here on our paper. Now, the experiment only works if you choose something that's relatively heavy. Okay? And I'll give you an example that doesn't work. My wife and I go biking. Sandy and I go biking, and she complains a lot when it's windy out. I don't complain when it's windy out. The reason she complains is that wind affects her more than it affects me. Why? Because she's so much lighter, the wind hits her and she has to pedal harder. I'm so big and fat it doesn't matter. Okay? Wind, no wind, I gotta pedal the same. Okay? Right? Have you see those people when they're out, the weather people? Okay, and they're out during a hurricane. And I'm here in the hurricane and it's blowing really fast and they're leaning into the wind. I'd be out there, I'd be like, yeah, I mean, I'm fat. I don't get affected by the wind, right? But they're so skinny, it does affect them. So you want to choose things that are relatively heavy to do the experiment. Bottom of the page. Subsequent experiments have confirmed Galileo's hypothesis that objects in free fall will fall with the same acceleration. Now, it says at the bottom there, it is still not known whether Galileo actually carried out his experiment. I don't know. I just thought he did. I thought he wrote about it. But I don't read Italian or Latin, so I don't know. Page 154. On Earth, if an object is dropped from a height, then the distance in meters it will fall in t seconds is given by the function t equals 4.9 t squared. Now I want you to notice something. It's not talking about how far it is compared to the Earth. It's talking about how far it is compared to the person dropping it. So when the person drops it, it always is getting farther and farther away. That's why the coefficient there is positive 4.9. So at 0, 0 times 4.9, what do you get? Let's fill in these values. So we've got 0. Well, 4.9 t squared. 4.9 times 0 squared is 0. 0.5, first table over here. 1, Jake, you guys, Nick. 1.5, Madeline, you guys. 2, Jessica. 2.5, back table. 3, Menominee. 3.5, we'll do together. So 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4. What did you get at 1? 4.9. Point 5, what'd you guys get? $1.5. Lauren?
I got, if this isn't right,
4.9.
11.025.
2.
I got 19.6.
2.5. How much?
625.
30.625? Menominee?
44.1.
3.5 we'll take. We'll take 3.5 squared times 4.9, 60.25, and then 4 squared times 4.9 is 78.4. So if we make, actually I should do this. I got to move my point, because if this is 10, 20, 30, 40, 50, 60, 70, 80, at 4 seconds here, I'm up to 80, close to 80. 3 seconds, I'm at about 44. 2 seconds, I'm at about 20. 1 second, I'm way down here. So my graph is going to be a half a parabola like that. So, how long would it take to fall 30 meters? About 2.48 seconds, something like that. The Leaning Tower of Pisa is 56 meters tall. So how long would it take for the ball to hit the ground? A little bit less than 3.5 seconds. Say 3.3 seconds. Something like that. Page 155. We are going to reverse a quadratic. So let's start with t. What's the first thing they did in our formula to t? They squared it, correct? And they got t squared. Then what did they do to it? Multiplied it by 4.9, and they got 4.9 t squared. And they said that 4.9 t squared is the distance. Oops, I forgot. This is times. So what's the first thing we're going to do to undo this quadratic?
Divide by.
Oh, very good. So divide by 4.9. So we get d over 4.9. Then what do we do?
Square root.
And when you square root, remember you get plus 4 minus square root of d over 4.9. So, if we wanted to find out the time, now here's how they write this as a function. I'm not real hep on the way they write it. So the inverse of the function is square root d over 4.9. And so if we wanted to know number 5, how long it would take to fall 56 meters, we would take second function square root 156 divided by 4.9, and we get plus or minus 3.38 seconds, which I said 3.3, so that's close. 3.38 seconds. Page 156. Now we're going to take D as our axis, and so you're going to fill in these values for the function dt. If D is 0, 10, 20, 30, 40, 50, 60, 70, 80. Well, if you take 0 divided by, so second function square root, 0 divided by 4.9, you get 0. So do 10, 20, 30, 40, 50, and 60, and give me your answers.
How many decimal places do you want us to go?
Just one. Ten, what'd you get?
1.4.
20.
2.
30.
5.
Somebody's got to get these answers. 40.
8.2.
2.2.
8.2.
8? No, that can't be. Too big. 2.9. 50, what'd you get, Menominee? Or no,
3.2.
60. So second function, square root, 60.
3.9. Or 3.5.
3.5. So our graph is going to look like that. If we graphed it on the same one as our other one, it will be just like the other one, but it will be, they call it symmetric to this axis right here. So if we folded our paper along that line, you would be able to see that these two are symmetric to each other. This is the function, and this is the inverse of that function. See you tomorrow.